Imagine that you have not a single gram of weight in your hands, and yet you run faster than lightning. Sounds absurd, right? But that is exactly how a photon lives. A particle of light that has no mass, but for some reason is not able to exceed the speed of light. For a long time, people dreamed of instantaneous movement. As early as the 17th century, the astronomer Rømer proved that light is not infinitely fast by measuring the delay in the arrival of light from Jupiter's satellites. Later, Maxwell's equations showed that the speed is not a random number, but a deep constant of nature encoded in the very structure of the vacuum. It turns out that the photon, although it has no weight, is bound by invisible bonds of the laws of physics. Today we know that if the speed of light were infinite, the world as we know it simply would not exist. There would be no causality, no known passage of time, no known image of events. Understanding why a weightless particle moves not faster, but exactly at a fixed speed, opens the door to the incredible world of quantum and relativistic physics, a world in which common sense often gives way to the majestic logic of the cosmos. If that paradox has you hooked, hit like to fuel our deep dives and subscribe to join the crew. We're chasing light to the edge of reality. Once people seriously believed that light propagates instantaneously, for how can one notice a delay where everything happens in the blink of an eye? This belief persisted for centuries, until in the 17th century one stubborn Dane decided to risk his name and reputation to answer a crazy question. What if light has a limiting speed? That man was Ole Rømer. In 1676, he observed Jupiter's moon Io. It seemed that its eclipses occurred with a noticeable delay when the Earth moved away from Jupiter, and conversely occurred slightly earlier when the Earth approached Jupiter. Rømer dared to draw a childlike conclusion. Light needs time to travel the vast spaces of the cosmos, and this time interval can be measured quite well. He estimated the speed at about 220,000 kilometers per second. It is not perfect, but for those times it was revolutionary. The world heard for the first time that light is not infinitely fast and thus has a measurable speed. Further, the story only got more complicated. In the 19th century, James Clerk Maxwell, armed with a theory of electromagnetism, derived equations which implied that the speed of electromagnetic waves depends solely on the properties of the vacuum, as well as electrical and magnetic permeability. This formula stunned the scientific world. Light is not a random flash in space, but a phenomenon strictly subordinated to the fundamental constants of the universe. Then came the era of precision measurements. The experiments of Fizeau, Michelson, and Morley showed that the speed of light in a vacuum remains the same for all observers, regardless of their motion. This fact became the cornerstone of Einstein's Special Theory of Relativity. Now, it was already clear that the photon, even without having mass, cannot be infinitely fast. It is bound to a fixed limit built into the very structure of space and time. This historical spark not only opened the way to 20th century physics, it forced people to rethink the very nature of time and distance. From that moment, the question of why a photon is not infinitely fast stopped being strange and became one of the key mysteries over which physics works to this day. At first glance, it seems, well, the photon has no mass. In nature, there are many particles with different properties, but in reality, this is not a caprice of nature, but a fundamental necessity without which the very logic of the laws of physics would collapse. Imagine that in the equations of the special theory of relativity, no particle with non-zero mass can reach the speed of light because it would require an infinite amount of energy. It is like trying to accelerate a car to such a speed that the speedometer needle would fly into space. The engine will simply burst, and the fuel will not run out only in mathematical fantasies. Photons, on the other hand, are born without mass and therefore do not accelerate. They instantly start from the set speed, as if fired from space-time itself. However, this does not mean that zero mass is a random mystery of nature. It is a requirement built into Maxwell's field equations and Einstein's energy equation. A photon can have energy and momentum even without having a rest mass. Try to give it even the smallest weight and the entire construction of physics will fall apart. Color would depend on frequency, not only in terms of hue but also speed. violating the principle of constancy. Furthermore, the zero mass of the photon guarantees that the equations of the electromagnetic field maintain invariance with respect to Lorentz transformations. If the mass were not zero, it would be necessary to rewrite all of electrodynamics, introduce new fields, and even revise the structure of quantum theory. Physicists have tried to check this in practice. The limit of the photon's mass is currently set at the level of 10 to the power of minus 50 kilograms. It is so small that on the scale of experiments, it does not differ from zero. So, zero mass is not a caprice, but a solid foundation on which both quantum physics and cosmology rest. Remove it, and fundamental laws collapse, and the world as we know it will turn into chaos, where light slows down or speeds up as it pleases. And nature, as a strict architect, is clearly not ready for such universal anarchy. If we try to explain the behavior of a photon without mathematics, the essence of the matter is simple. Every particle possesses energy, which consists of two components: rest energy depending on mass, and kinetic energy related to momentum. In the case of massive particles, the first part is always present, and the larger the mass, the harder it is to accelerate to high speeds. In the case of a photon, which is massless, rest energy simply does not exist, and all of its energy is contained in motion. But that is the trick. It is precisely this property that makes its speed invariant. In the world described by the theory of relativity, the laws do not allow particles without mass to move slower or faster than the set limit. No tricks, no cosmic life hacks will help. This is not a race where you can add fuel and overtake competitors. If a particle has no mass, it always and everywhere moves at only one speed: the speed of light in a vacuum. Look at it from the other side. If a photon could change speed, we would observe strange effects. Rays of different colors and thus of different energy would reach us at different times. Let's say that during the explosion of a distant supernova, blue light would arrive earlier than red. However, astronomical observations say otherwise. All photons, regardless of their energy, arrive synchronously. This fact is so certain that it is used to check fundamental theories, including experiments with gamma pulses and neutrino observatories. Therefore, no schemes with formulas are possible. The laws built into the fabric of the universe work without exceptions. If mass is equal to zero, speed is strictly fixed. In this sense, the photon resembles the ideal clockwork mechanism of the cosmos. It always moves exactly as it should, without the slightest deviation. In the world as we know it, everything can stop. A stone can be placed on the ground, a train can be stopped at a station. Even a particle such as an electron can stop at a specific point, relative to us if we choose the right reference frame. But in the case of a photon, this trick will not work. It does not and cannot have a state of rest. It is always and everywhere in motion. To understand why this is so, imagine that we are trying to catch up to a photon by moving alongside it. In our intuitive imagination, we simply increase speed until we are next to this particle of light, and behold, it has stopped next to us. But in reality, it is not so. According to the laws of the Special Theory of Relativity, it is impossible to create a reference system that moves with the speed of light. For every observer, no matter how fast they might be, the photon will always fly past with the same speed. It is not a matter of technical limitations, but a fundamental prohibition of nature. But this is not the end of the oddities, because since the photon always moves at the same speed, time in our understanding simply does not exist for it. In its personal universe, the moment of emission and the moment of absorption merge into one single present. For a photon, the journey from a distant star to our eye, even if it takes millions of years according to our clock, takes no time at all in its own reality. It seems to move without breaks, bypassing the very idea of time. This feature has far-reaching consequences. Firstly, it explains why a photon cannot be caught or slowed down in a vacuum. The only thing we can do is change its trajectory or interact with it through absorption and re-radiation. Secondly, it is directly related to the fact that the photon does not have its own coordinate system. All laws of physics are described exclusively from the perspective of observers moving slower than light. Interestingly, even modern experiments such as slowing down light using a laser in special environments or quantum manipulations of photons and optical traps, do not change this fundamental fact. In a vacuum, the photon always and invariably moves at the same speed. This property depends neither on its color, nor its energy, nor the distance it covers. As a result, a paradox arises. For us, a photon is a traveler flying billions of years through the cosmos. But for it, the path has no beginning or end, one moment in which there is no before and after. And that is precisely what makes light such an exceptional phenomenon, serving simultaneously as a bridge between space and time, and the key to understanding the structure of the universe. At first glance, it sounds like physical absurdity. How can something that has no mass carry energy and even exert pressure? But that is exactly how a photon works. It is simultaneously weightless and capable of performing quite real work. A photon is a quantum of the electromagnetic field. Its energy is directly related to the frequency of the field's vibrations. The higher the frequency, the more energetic the photon is. This is exactly why ultraviolet radiation is more dangerous for the skin than infrared radiation. Every quantum of it contains more energy, and yet it has not a single gram of rest mass. This energy is expressed in the form of momentum. And momentum is what allows a photon to exert pressure, however incredibly small. In space, this effect is particularly clear. Sunlight reaching space sails is able to slowly but effectively accelerate them. This is how the idea of a solar sail works. No engines, no fuel, just billions of photons, each of which, hitting the surface, transfers a small impulse. It seems ridiculous on the scale of one photon, but on the scale of a stream of sunlight, it turns into a perceptible force. On Earth, we encounter this every day. A photon hitting a surface can heat it, transferring energy to the molecules of the substance and causing them to vibrate more strongly. This is exactly the way sunlight heats our world. This same principle lies at the base of the photoelectric effect, for the discovery of which Einstein received the Nobel Prize. Light is able to knock electrons out of metal if the energy of individual photons exceeds a certain threshold. Even in the depths of cosmology, the energy of photons plays a key role. Cosmic microwave background radiation, the faint, almost invisible background light remaining after the Big Bang, permeates the entire universe and carries information about its early stages. A photon that was created over 13 billion years ago still preserves this ancient energy within itself today, and all this with zero mass. Nature tells us, mass is not the only way to have weight in the physical world. Energy and momentum are capable of working wonders, even if there is no matter in our traditional understanding. And in this lies the astonishing elegance of the structure of the universe. A void can in reality be full of power if photons fly through it. Many people are used to thinking of a vacuum as a bottomless void, completely deprived of any medium. However, 20th century physics destroys this naive image. Research shows that a vacuum is not an emptiness, but a boiling quantum arena, where virtual particles and antiparticles instantly arise and disappear. And precisely this turbulent, invisible activity imposes a fundamental limit on the speed of light propagation. The speed of light is not a random number, but a kind of resonance of the vacuum structure. Photons traversing space constantly interact with quantum fluctuations, virtual electron-positron pairs that for the shortest moment arise from energy and are immediately annihilated. These microscopic collisions do not slow down light in the usual sense, but they create the physical constant that we know as the speed of light. Physicists call this the vacuum polarization effect. It was seriously considered for the first time within the framework of quantum electrodynamics when it became clear that even an absolute vacuum behaves like a specific environment with its own properties. If there were no fluctuations, photons would move instantaneously, but then the very structure of spacetime could be destroyed, and the laws of physics would lose their meaning. Moreover, there are bold theories suggesting that in extreme conditions, for example near black holes or in the early universe, the speed of light could have been different. Some cosmological models even use the variable speed of light hypothesis to explain the mysteries of the Big Bang. However, in our modern cosmos, the quantum vacuum is stable, which means that the speed of light is a built-in limit, a kind of link to the fundamental order of the universe. As a result, a paradox reappears. Light moves at the maximum speed, but precisely this maximum speed is not infinite, and it results from the deep structure of reality itself. For decades, physicists have proceeded from the postulate that the photon is a massless particle that always moves at the speed of light. This claim has withstood all tests, but there is a certain nuance. In science, absolute zero is rarely the final verdict. Every measurement has limits of accuracy, and therefore the mass of the photon, if it exists, may have such a negligible value that we are simply not yet able to detect it. Modern experiments chase this phantom with incredible ingenuity. Some look for clues in the change of the speed of light during its passage through intergalactic space. If a photon is slightly heavier than zero, it will slow down depending on its energy. Others analyze the magnetic fields of planets and even of the galaxy itself, because the mass of a photon would change the way these fields propagate in space. But here a problem arises. Even the most accurate laboratory devices and cosmic observations have not shown the slightest deviations from the theory of masslessness, if one can call it that so far. The upper limit of the photon's mass, set as of today, is so small that it is hard even to imagine. It is 1,000,000,000,000 times smaller than the mass of an electron. It is like trying to weigh a snowflake that fell on an iceberg. Even super-sensitive scientific scales may not catch such a signal. And yet, if it suddenly turns out that the mass of the photon is not zero, the consequences will be truly amazing. Electromagnetic radiation will cease to be infinitely long-range. Maxwell's laws would require revision, and the fundamental symmetries of nature would be violated. Moreover, it would be necessary to rewrite cosmological models, because the evolution of the universe in the early epoch would have proceeded differently. This is one of those cases when a small correction in a decimal fraction can change the whole picture of the world. The history of the search for the photon's mass is not only a narrowly specialized scientific experiment, but a true detective mystery in which every measurement can overturn our idea of the fundamental laws of nature. At first glance, it seems that the result is predetermined. The mass is zero, but reality is more complex and much more intriguing. Even the smallest suggestion of non-zero mass can reveal an entire layer of new physics, from the revision of Maxwell's equations to the redefinition of the structure of the universe. Over decades of research, humanity has approached the limit of instrument sensitivity, where the difference between zero and a microscopic value is thinner than the boundary between noise and signal. Here, every result becomes priceless. Zero is a confirmation of the consistency of the standard model, and a non-zero value is an invitation to the unknown, where perhaps new fields, particles, and interactions are hidden. One can say that the race for the photon's mass is a test of how we are able to ask ourselves uncomfortable questions. And until we find the final answer, one thing remains for us: to continue observing, experimenting, and being ready for the universe to surprise us again at the most unexpected moment.